In this video, we're going to be talking about free radical chemistry and stability and how we can use the structure of a radical to predict its relative reactivity and stability. So when we talk about free radicals, this means we are talking about unpaired electrons. If a carbocation is lacking 2, a carbanion has 2 excess. This is going to be in this class specifically a carbon that has one unpaired electron. As you can imagine, if it has unpaired electrons, it's going to be an odd number of electrons. That most of these free radicals are unstable. They're also neutral species. They're neither cationic nor anionic. And looking at the structure of a radical species, if we draw, our planar sp2 hybridized species, we have our unhybridized p orbital above and below the plane, and that's where our radical will live. So free radicals are sp2 hybridized with the lone unpaired electron lying in the perpendicular unhybridized p orbital. As we talk about stability of radicals, we can see a similar trend to those as we do see with carbocations. So as we can imagine, as we increase substitution around, so this is our radical here, as we increase substitution around our particular radical due to things that we've mentioned before, like hyperconjugation and inductive effects, we can increase the stability as we go from a methyl to a primary to a secondary to a tertiary radical. So we are increasing stability as we go from methyl to tertiary. So this is our stability. And that's due to such things like hyperconjugation and inductive effects, which we've mentioned before. Now, the arrow pushing, when we draw mechanisms for radical reactions, is a little bit different because we're no longer talking about 2 electrons moving at once, but we're talking about 1 electron moving at once. So let's compare the arrow pushing between 2 electron pushing and 1 electron pushing. So for 2 electron pushing, we're often talking about heterolytic cleavage of a bond. So heterolytic cleavage of a bond means 2 electrons go one way. So they're moving in one direction. So if we, for instance, have HX, and as we've seen, this could be like HCl, we see our arrow pushes, here let me make this a different color, our arrow pushes from the X, or from the bond to the X. So that means our 2 electrons will end up on our X. So this is what we refer to as heterolytic cleavage because we end up with a cation-anion pair. So we've gained 2 electrons on X and we've lost 2 electrons on H. Now the opposite of this, and what we see in radical chemistry, is homolytic cleavage of bonds where 1 electron goes each way. So the arrow pushing for this is a little bit different. Instead of using these one direction double-headed arrows, we're actually going to have 2 arrows coming from the bond, and they're going to be single barbed arrows, so to show that there's 1 electron flowing in each direction. So this bond, as we know, a single bond contains 2 electrons. One of the electrons will flow onto X, and one of the electrons will flow onto H. And as a result, we're left with 2 radical species, an H dot and an X dot. They are both neutral, and they're both radical species that we've now gained from homolytically cleaving that bond. We use this single-headed arrow when we're talking about radical chemistry to show that 1 electron is flowing rather than 2. In a species with multiple places that can form a radical, we often have to determine where a radical is most likely to form. So, for instance, if we look at this species here, we have 3 locations we can form a radical. We can abstract an H here, we can abstract an H here, or we can abstract an H here. So let's look at these 3 possibilities. So let's look at first this H being abstracted. So if we abstracted that H, we say we broke that CH bond homolytically, we'd form a terminal radical. Okay. Let's examine the next possibility. We'll look at this one. So if we abstract that H and we homolytically break that CH bond, we'd form that radical, and this is, of course, with an H radical that's formed in conjunction. And finally, if we abstract that 3rd hydrogen, we'd form this radical here, and again, plus H dot. Examining which one of these is most likely to happen, we have to look at the type of radical that's formed and examine the stability trends. So in this case, this radical formed here is primary. In the second case, we have a secondary radical. In this third case, we have a tertiary radical. So when we're thinking about which one of these radicals is most likely to form, we understand that primary is less stable than secondary, which is less stable than tertiary. So if we were to abstract one hydrogen, we would most likely form this tertiary radical here. Because it's stabilized both by hyperconjugation. In this case, hyperconjugation will stabilize that radical. So this tertiary radical is most likely to form. It turns out that we can form even more stable radicals when we exhibit resonance. So let's say we look at this structure here. Now, the two most obvious H's that we could abstract are these two here. Now, you could, in theory, guess that you could abstract two further hydrogens from these positions, but recall that an sp2 bond, an sp2 CH bond is much stronger than sp3 CH bond, so the energy required to remove these hydrogens is going to be much too great in most radical-based reactions, so those won't form radicals. Those sp2 radicals will not form because those sp2 CH bonds are too strong. So let's examine these two cases here where we abstract these two hydrogens from sp3 situations. So let's first examine this terminal case. So if we abstract the hydrogen, we form the primary radical. Now we already know that primary radicals are not as stable, but we can see what happens if we abstract the other hydrogen. So if we abstract the other hydrogen, we form the secondary radical, which in just comparing these two, we understand that the secondary radical is more stable than the primary radical. But if we look at this double bond, we can also display some kind of resonance structure where, say, we push, and this is again single-headed arrows, we form the double bond here and we push one electron onto the terminal position, and we form a resonance structure which has a terminal radical here. Now, again, secondary radical is more stable than the primary radical, so this first species is what will dominate in this resonance, but resonance does stabilize the radical as we get some kind of resonance hybrid that would have the radical displayed over a range of carbons, further stabilizing it by resonance.